Hi, I'm Shahnawaz. In last lecture, we characterized the morphisms between varieties. So we proved that if x and y are varieties with y in the affine n space, then a map phi between these varieties x and y. So this is a morphism. If this phi is given by n tuple of polynomial functions, that is, if this phi is given as uh, say f1 up to fn, which means that phi of p is same as f1 of p up to fn of p, where these fi's they are regular on x, so they are regular functions. Now we so this is the if and only condition. So if this phi is given like this, then phi is a morphism, and if phi is a morphism, then we can write this phi as this n tuple of regular functions. We have a consequence of this result. So it states that say x is in an and y in am. So suppose they are closed subvarieties. Then the morphism phi from x to y are precisely the polynomial maps. So then the morphisms between say then the morphisms phi from x to y, so they are precisely the polynomial maps. So they are precisely the polynomial maps. So let us first recall what do we mean by a polynomial map. So suppose x and y are the closed subvarieties. Say x is inside an and y is inside am. Then a polynomial map between x and y is actually an m tuple of polynomials, say f1 up to fm. Let us write these polynomials with by uppercase letters. So f1 up to fm. So this is a polynomial map from x to y, where this map sends a point p inside x to the m tuple f1p up to fmp. So in a polynomial map, a polynomial map is given by this tuple of polynomials, and a morphism is given by this tuple of regular functions. So in case these x and y are closed subvarieties, then there is no distinction between the regular, I mean the morphisms and polynomial maps. So this result follows easily from the fact that the regular functions on x is actually same as the coordinate ring of x. So proof. So the result follows immediately from the fact that the regular functions on x is same as the coordinate ring of x. I mean the so we can identify this ax with the polynomial functions on x. So this gives a proof. Now we want to show that there are more affine varieties than just the closed subvarieties of an. So for that we'll first define what do we mean by the principal open of a polynomial. So we have this definition here. So let us consider x to be in n. So let's suppose x be a closed sub variety. And let us consider a polynomial f inside the polynomial ring n variables, say x1 up to xn. So this f is in the polynomial ring but is outside the vanishing idle of x. So this means, so if f does not vanish on x, that means this x is not contained in the zero set of f. So then the principal open defined by f. So then the principal open defined by f. So it is actually principal open defined by f is actually a polynomial. So this is I mean, sorry, this is actually a set denoted by xf, which is the set x except the zeros of f. So this is actually the complement of the hyperspace zf in x. So this xf is called the principal open defined by this polynomial f. So this is actually a subset in an, because it is a subset of x, and x is itself a subset of an. Now we have a proposition which says that this principal open defined by f is actually an affine variety. That means this x sub f is zero set of some ideal in the polynomial ring. So this is what we have to prove. So we have a proposition. So x f, let us first let us write this in with more details. So let x in an be a closed subvariety, and let f be a polynomial which does not belong to the vanishing idle of x. Then the principal open defined by f is an affine variety. By affine variety we mean if it is of the form, I mean, if we can write x sub f as the zero set of some polynomials. So this is an affine variety. Let us prove this. So let us consider a set, say z, which is I mean the zero set of the ideal of x and the polynomial uh, f times xn plus 1 minus 1. So note that this is going to be an affine variety in an plus 1, because now we have polynomials in n, I mean in n plus 1 variables. So this is a subset of an plus 1. So we want to show that this z is a closed subvariety of an plus 1. I mean, we want to show z is isomorphic to the so we have to prove x sub f is an affine variety. That means we have to prove it is zero set of some polynomial. So if we prove that it is isomorphic to z, that means z being an affine variety, so then we are done. So we want to show z is closed subvariety isomorphic to the principal open of f. So for that we have to exhibit a morphism between x f and a n plus 1, I mean or z. So that phi be a map which is given by this polynomial map or the morphism x1 up to xn and 1 over f. These are the regular functions. So from the set x sub f to an. So note that these xi's, they are all coordinate functions and hence are regular on x. Also, uh, this xf contain all points in x where f ceases to be 0. Therefore, 1 over f is also regular on xf. So this shows that this phi is a morphism because we know uh, uh, phi is a morphism if and only if it can be, I mean, expressed as an n tuple of regular functions or some tuple of regular functions. So note that xi's while I goes from 1 to n are coordinate functions and hence uh, are regular on x. And in particular on xf because x sub f is contained in x, so they are regular on x sub f. Also, in this x sub f uh, contain all points in x where this f is non-zero, I mean where f ceases to be 0. Therefore 1 over f is also regular on x sub f. This shows that phi is morphism. This shows that this phi is a morphism. Now, what we want to prove? We want to prove phi is an isomorphism between x sub f and z. So if we look at the image of this phi, it is exactly the z. So it's exactly z. But first, note here phi is morphism because it is given by this n plus 1 tuple of regular functions. So note that the image of phi, I mean the phi of x sub f is, so since phi is a morphism from x sub f to an, so this is actually uh, z. Now why this is z? So if we look at z, uh, it is a set of all points, I mean set of all n plus 1 tuples a1 up to an plus 1 in the f1 an plus 1 space, where these a1 up to an are points in x sub f, and an plus 1 is of the form, I mean where an plus 1 is 1 over f times a1 up to an. So that is the reason that the image of phi is exactly z. Now we want to prove this phi inverse, I mean, which is a map from z to x sub f. I mean, we want to prove phi between these two sets is a bijective map. So also phi from x sub f to z is bijective. Now why this is bijective? So surjective is understood because the image of phi, uh, the image of x sub f under phi is exactly z. So surjectivity is clear. So for injectivity, so if we look at it as inverse, I mean phi inverse from z to x sub f, that is actually the projection to the first m coordinates. So that is the reason that it is injective. So this is the bijective with inverse. So let us write this inverse by phi to the minus 1 from z to x sub f. So this is given by the projection, by the projection to first n coordinates. First n coordinates. So moreover, this phi, I mean this x is uh, irreducible. So moreover, x sub f is irreducible. Now, for if it is not reducible, so for if not, sorry, not xf, we want to show z is reducible. So for if not, let us suppose that this z is equal to the union of two, could also say z1 and z2, where, I mean, where this zi is properly contained in z, and these zi's are closed, they are closed. So then if we look at the inverse image of z, that is the inverse image of z1 union inverse image of z2, because this phi is given to be bijective with, if we look at phi inverse of zi, that is properly contained in uh, I mean x sub f. So this shows that this x sub f is reducible, but x sub f is not reducible because x is not reducible. X is given to be a closed subvariety. So x being a closed subvariety means X is irreducible. This shows that why this is properly contained inside X sub F, because Zi is properly contained in Z. So if this is the case, then the inverse image of Z is properly contained in inverse image of, the inverse image of Zi is properly contained in the inverse image of Z, which is X sub F. So this shows that X sub F is reducible, which is not the case, since uh, X is a subvariety. Hence, Z is a closed subvariety. So we are good so far. Now it remains to prove that this phi inverse is also a morphism. If we prove that this phi inverse is given by some, say, m tuple of polynomials, then we are done. So also, if we look at phi inverse, which is a map from z to x sub f, so it is given by, I mean, it is given by the coordinate functions. These coordinate functions which are regular. So this is from z to x sub f. So this phi inverse is given by the projection to first n coordinates. So obviously this is a morphism, since each xi is a regular function on z. So this is a morphism. Hence, z and x sub f are isomorphic. But this z is zero set of some polynomials. So that means z is an affine variety. So that now z and x sub f being isomorphic, this would imply x sub f is also an affine variety. So hence x sub f is an affine variety. Now, in last lecture we studied morphisms to affine varieties. Now here we are going to study morphisms to quasi-projective varieties. But before that, let us recall that we can cover this projective n space by open status, say ui, where ui contain all the points in projective space, say a naught up to an. So they are the elements of Pn whose ith coordinate is non-zero. So we know these are open sets in Pn, and with the help of these open sets, we can cover this Pn. Then we defined a map phi I from Ui to An. We define the maps from these open sets to affine space by mapping the point a naught up to an to the point uh, a naught by ai, so on, ai by ai. Let us write a cap here to emphasize that this coordinate is not there, this is omitted. So this is an by ai. So now this is an m tuple, so obviously this is point, this is a point in an. So we know this map is a bijection with the inverse, say psi I. So psi I is a map from an to ui, which takes a point, say a naught up to ai cap. So this cap here means this term is not there, this is omitted. Similarly, this head over here means this term is not there. So up to an, so this mm, point is mapped to the point a naught, so on 1, so on an. So this one is at the ith coordinate. So this pi is a bijection with psi I being it is inverse. Now we want to show that this map phi is an uh, isomorphism. So we want to prove this phi is an isomorphism. That is, we have to show phi as well as psi I are both morphisms. Now to prove this result, um, so actually, we want to prove in particular that every locally closed subvariety of an is isomorphic to a quasi-projective variety. So to prove that, we first prove this. I mean, this ui is isomorphic to an. So by proving this, we will be able to prove that any closed subvariety of an is actually isomorphic to the projective variety. Now, to prove this result here, we are first going to prove the dehomogenization of a polynomial. So we have this definition. So let us consider a polynomial, say f, in the polynomial ring, say in n plus 1 variables. So then the dehomogenization, then the dehomogenization of f is given by, so we write the dehomonization of this f. So it is actually a polynomial given by f sub a. So this polynomial is in n variables. So this is same as the polynomial f, but we just take the, we just eliminate one variable. So let us eliminate the first variable. So then we are left with n variables. So this is a polynomial in n variables. So this is what we mean by dehomogenization of a polynomial. So now let's prove the theorem. So let ui in Pn be open such that ui contain all the points in the projective n space whose ith coordinates are non-zero. So then in the map phi from ui to an. So this map is given by, so we take a point ui inside, I mean we take a point, say a naught up to an inside u, and this point is mapped to the point a naught up to ai, so on ai up to ai, so on an up to ai. So we want to prove that this map is an isomorphism. Let us prove this. So without loss of generality, we may assume that I is zero. So without the loss of generality, we assume I is zero. And we write this U with U, I mean U naught with U, and we put phi to be equal to phi 0. Then this phi is given by, so then phi is given as, so we can write this phi as the map given by these coordinate functions. So now one can note here that xi over x0, while I is running from 1 to n, is a quotient of two polynomials of same degree, and the denominator does not vanish on u naught. So thus each xi over x0 is a regular function on u. So that proves phi is a morphism, because we are able to write this phi as some tuple of regular functions. So note that uh, if we write this quotient xi by x0, where this I goes from 1 up to n, so this is a quotient of two polynomials of same degree, and the denominator, I mean x0, does not vanish on u, which is u sub 0. So thus phi is a morphism. So thus phi is a morphism. Now to prove phi is an isomorphism, it remains to prove that its inverse is also a morphism. So let psi be the inverse of phi. So we wish to prove that this psi is, so this psi is actually a map. So it's a map from A and to U. So we wish to prove psi is also morphism. Now here we are going to prove this formally, I mean by definition of a morphism. So to prove psi is a morphism, we have to show it is continuous and it preserves regular functions. Now for continuity, it suffices to prove psi pulls back uh, closed sets to closed sets. That is equivalent to prove phi is a closed map. So we claim, so our claim is that psi is continuous. So for that, to prove psi is continuous, we have to take a closed subset inside U, and we have to look at its inverse image. So let say W, which is zero set of some polynomials, say f1 up to fn, intersection U, where so where these fi's, they are polynomials in n plus 1 variables, be a closed set. So they are, these polynomials are homogeneous as well, where these fi's are the polynomials which are homogeneous. Now let us look at the inverse image of W under psi. So psi inverse of W is the set of all m tuples, say a1 up to an, inside an, whose psi images inside W. So that is the set of all m tuples in an such that this uh, but psi of a1 up to an, so this is given by uh, so we forgot to mention here, so why the psi is given by, so it takes an m tuple and it maps it to the point 1 a1 up to an. So this follows from this fact, because we say phi I has inverse psi I. So for I is equal to 0, we do not here phi 0 by phi and psi 0 by psi. Sorry, psi. So this psi takes an n tuple and it maps to the, it maps n tuple to this point where the first coordinate is 1. So psi of this point over here is the point 1 a1 up to an. So this has to be a point inside W. So this is the same set, the set a1 of all points in an such that now the point 1 up to 1 a1 up to an will be inside W, but W is given to be, so one can look over here, this W is the zero set of the polynomials f1 through fm, so this W is given like this. So a point will be inside W if uh, each polynomial fi evaluated at that point vanishes. So that means if fi vanish when we evaluate this at point 1 a1 up to an. So for all I equal 1 up to m. So this means this is the set of all points in the fin space such that, but this is same as if we first dehomogenize fi, then we evaluate this dehomogenized polynomial to the n tuple for all I goes from 1 to m. So it's the same thing, or this is same as to say that this is the zero set of the dehomogenized polynomial f1 up to dehomogenized polynomial of fn. So this means this is a closed set in an. So this is closed in an. So we proved that this uh, psi pulls back um, closer status to closer status. So which proves that phi inverse is continuous. So hence psi, which is same as phi inverse, is continuous. Now, by definition of morphism, it remains to prove that this psi pulls back. I mean, this psi preserves the regular functions. So for that, so finally, let us consider, say, V to be an open subset of U, and let us take a regular function on V. So we have to prove, we have to show that we have to show that the psi star composed with H, which is H composite psi, is an element, I mean, is regular on the inverse image of V. So this is what we have to prove. Now, so if necessary, we can make V smaller, and we can write H as the quotient of two polynomials, say f and g, which are homogeneous and of same degree, such that the denominator does not vanish on V, psi inverse V. So by making V smaller, so this is, I mean, this we can do this if it is necessary. So if necessary, so we can make V smaller, and we can write this H as a quotient of two polynomials, say f and g, and these two polynomials, so they are homogeneous and of same degree. So they are the elements of the polynomial ring x0 up to xn. So they are the forms of same degree, such that this g is non-zero only. If this g is non-zero, I mean, this is non-zero on V. So then we can write psi star h as h composite psi, but h is given to be the quotient of two polynomials, so we can write this as f composite psi over g composite psi. So but if we look at the, so but f composite psi, so if we evaluate this map at points say a1 up to an, so this gives us f of psi of a1 up to an, which is the point 1 a1 up to an. So this is the uh, dehomogenized polynomial f sub a evaluated at the point a1 up to an. So we can write this psi star h then as the quotient of dehomogenized polynomial f sub a mod g sub a, because same is the case with g sub a. So, and these dehomogenized polynomials, they are regular on the inverse image of v. So since this GA has no zero on V. So this means that psi is uh, continuous, and hence psi is a morphism, which means phi inverse is a morphism. So hence phi inverse is a morphism. Thus phi from UI to AN, let us call this I here, is an isomorphism. In other words, each projective, open set UI is isomorphic to the affine n space.